Hello everyone. So I'll be talking about modeling spin precessing binaries using the twisting approximation, a systematic accuracy assessment. So this is an ongoing work with Samanya, Prayush, Vaishak at ICTS and other collaborators in different places. Okay, so gravitational waves are the ripples in the spacetime that's created by the merger of compact objects. So here are some movies by SX's collaboration and LIGO Galtech that's showing that two compact objects like black holes, they're spiraling around each other and eventually they merges. And this gravitational wave travels far and then reach our Earth. So when gravitational wave passes through Earth, you see there is some distortion in the spacetimes around Earth, and you measure that gravitational wave strength using some detector that we have called LIGO detector. Now, there are different stages of binary black hole evolution. So if you have two black holes with different masses and different spins, so initially they will be spiraling around each other for a long time, and then they come close to each other. They radiate the gravitational waves, and then they merges, and eventually you get a final black hole with some mass and spins. So here I'm showing the waveform that it looks like. So in the inspiral region, you can see the waveform, and as it eventually the black hole comes near, it merges and the gravitational wave amplitude also increases, and then finally you see some quasi-normal oscillation in the ring-down mode. So to model these different stages of binary evolution, you use different semi-analytical waveform model or approximation methods. So to model this in-spiral part, you use something called post-Newtonian theory, which is basically adding some post-Newtonian correction to your Newtonian equation, and you solve the equation to get the dynamics in that region. And then for the ring down part, you use some kind of black hole perturbation theory to model those quasi-normal mode in the ring down part. And there comes the merger part, which is very highly dynamical, and no, like any analytical model like this cannot model this part of this merger. So you need this called numerical relativity simulation, which basically solves the full Einstein equation to give you the last few cycle or the merger part, and which is very highly accurate. But the caveat is that this numerical relativity simulation are very expensive, and it can take like weeks to months to just give you one waveform for few cycles. So that's why we need different analytical waveform model. So just to say, so this binary, they can form in different channel. So popularly there is two channel that you can divide. One is called isolated, another is dynamical. So in the isolated channel, let's say two stars, they're in binary, and then they evolve, they goes into supernova explosion, they becomes black hole, and eventually they merges. So in that process, if there is some initial eccentricity in the orbit, that because it goes through all this time period, the eccentricity eventually circularizes, and by the time you get the signal in the LIGO detector, you don't see any hint of eccentricity. Also because it's isolated system, so it's expected that this kind of system will have non-spinning or aligned spin. Aligned spin means the spins of the two black holes, they are aligned or anti-aligned with the orbital angular momentum. And there is another formation channel called the dynamical formation channel, where it can happen that the two black holes, they are in the binary in the dense globular cluster. So there are other stars and other black holes that can affect the revolution. And in these cases, the neighboring black holes or other objects in your globular cluster that can affect your binary evolution, and it induces some eccentricity in the orbit. Also, there can be some spin precession, which is like having spins of the black hole that is not aligned with the orbital angular momentum. And in your gravitational wave modeling, you want to incorporate as much physics as you can, like adding this precession and eccentric, because this gravitational waveform, they are basically used to analyze the data that you get in the detector and infer the source properties. So the more accurate and more physics you can put in your waveform model, the better, the less biases you will get in your analysis. So okay, let's talk more about these precessing binaries. So here I have two movies by SXS collaboration, especially by Vijay. So the first movie is about the aligned spin binary. So here you are seeing two black holes, they have spin which are aligned or anti-aligned with the orbital angular momentum, and it evolves and the gravitational waves look something like this. It's the amplitude is increasing monotonically, and eventually it merges and you see the gravitational wave. And okay, so and there is this precessing system. Here, the two black holes, they have spins that are not aligned with the orbital angular momentum. So in that case, you are seeing the orbital plane itself precesses over time. And you see these imprints of this precession in your gravitational wave by some modulation that was not present here. So this gravitational waveform H can be decomposed in different harmonic mode, spherical harmonic mode called HLM. And here I'm plotting a waveform from this aligned spin waveform mode. So you can see, as in the movie I showed the gravitational waveform, the aligned spins are the direction of the orbital angular momentum is always fixed. So you can see the amplitude is always increasing. But for the precessing system, there is this extra modulation due to this precession as the orbital plane precesses. Also, another thing about this waveform modes is that there is a mode hierarchy for a non-precessing system. So here you can see the 2-1 mode amplitude is very low compared to the 2-2 mode. But here, due to the precession, there is a mode mixing, and some energy from the 2-2 mode can transfer to 2-1 mode. And you can see some here the 2-1 mode, the amplitude is very comparable to 2-2 mode. So yeah, so due to all this effect of this precessing waveform, that is like complex time-dependent orientation of the system, it has modulation in the amplitude and phase. Also, precession timescale is different compared to the orbital timescale and the radiation timescale. So due to all this complexity, it's difficult to model this kind of system analytically. So we use some kind of approximation method to do that. So what we do is that we take a precessing system, we transform it into a co-precessing frame. So co-precessing frame is a non-inertial frame which tracks the precession of the orbit. So essentially in that frame, the waveform looks like a non-precessing waveform. So there are different definitions of the co-precessing frame, how we can track the precession of the orbit, but eventually if you see the waveform, I took a precessing waveform, there is this highly modulation in the amplitude, but when you transform it to the co-precessing frame, you see it becomes less time varying. And there is another approximation that says that this co-precessing waveform mode can be identified or approximated by this aligned spin waveform mode. So here I'm showing that. So if you have a precessing waveform mode, let's say any mode, you can use some rotation to transform it to a co-precessing frame. And then you can just do the inverse transformation. Let's say you have a co-precessing waveform mode, you can just use the inverse rotation to get a precessing waveform mode. And now, as I said, this aligned spin and co-precessing waveform mode, they can be identified with each other. So you can put a, you can take a aligned spin waveform and then construct your approximate precessing waveform mode in that sense. So which we call the twist up. So it eventually is essentially you take aligned spin waveform mode, you apply the inverse rotation, you twist up, and then you get the approximate precessing waveform mode. So this is the approach that the modeling community used so far to model these precessing binaries, but they have been tested on like the LIGO detector, which is sensitive here. So here I'm showing a sensitivity curve of different detector. So currently we are in LIGO era, and there is some future plan of Voyager and Cosmic Explorer, Einstein telescope. So those are much more sensitive, you can see the scale, and those also can probe to the lower frequency. So as you increase the detector sensitivity, you want much more accurate waveform model so that your systematic error is not greater than the statistical error of the noise curve. So how do you check that? So we take a precessing waveform mode, we apply some rotation to get the co-precessing waveform mode. And then we identify the co-precessing waveform as an aligned spin waveform. And then we apply the inverse rotation to get our twisted aligned spin. And finally, we try to see how much this twisted aligned spin waveform mode overlap with the actual precessing waveform that you started with. So we calculate something called match, which is a normalized inner product of two waveform, that is like noise weighted inner product of two waveform. And if you have match, you can also calculate mismatch. And in the modeling for LIGO detector, we say if the two waveform has match more than 97%, then we say they are identical. For my study, I'm using some waveform model called inert surrogate waveform, inert search 70K4, which is a surrogate model that uses inner data to interpolate and create the surrogate. So here are some result. So this is mismatch result, mismatch of this actual precessing that I started with and the twisted alignment that I call the approximate precessing waveform mode for a quasi-circular binary, and this is for 2-2 mode. So there is a lot of information here, but just for now, just focus on the first column. So I'm plotting the mismatch of this approximate precessing and the actual precessing I started with for two detector, LIGO and Cosmic Explorer, that is the third generation detector. The color bar shows the spins, magnitude of spin for the primary object. So you can see as the spins are very low, the mismatch of this approximate waveform is very good, like it's below 10⁻⁴, and that is very good for our current detector and future detector. But as you go to high spin case, the mismatch increases and it can go to like 3% for LIGO, and for C there is some point that is above 3%. So this is good. This is good in the sense that this twisting approximation is working well for our current generation detector, and we can get almost for all the sample point the mismatch below 3%. But for Cosmic Explorer, that is not enough. We need more accurate waveform. Okay, so I also studied this for eccentric binaries. So okay, just the result where we get here. So this x-axis shows the different modes mismatch, and y-axis the mismatch value. So you can see for the 2-2 mode, for most of the cases, the mismatches are below 1%, like 10⁻². So that shows like for 2-2 mode, at least it's good. But for higher mode, the mismatch, if you see the 3-1, 3-2, and higher mode, the mismatches are above 1%. So yeah, we need to worry about that. Okay, so I'll conclude here. So yeah, accurate gravitational wave modeling is becoming much more critical as the detector sensitivity improves, and this twisting approximation that we use to model the precessing binaries, which is good for LIGO, but the accuracy is not good for the Cosmic Explorer, which is the third generation detector. And for eccentric binaries, the approximation maintain the 3% threshold for 2-2 mode, but for our higher mode, we need to uh, study more because the accuracy is not better for the higher mode. So thank you.
So we have 3 minutes for the questions. Are there any questions here?
So I was wondering this particular approximation that you're saying, like how controlled is it? Is it like something where we can calculate the first corrections? Like, you know, is there some theory where I can calculate, where I can say, for example, that it would have been 3% off and so on?
So we do that by comparing this approximate waveform with the NR data we have. We have some NR data for few sample point. So NR data, because you solve the full Einstein equation there, so we consider it is the much more accurate. So we compare this approximation with the NR data, and we then validate our model how accurate it is.
Yeah, so this I understand. You're comparing with the numerical data, but I'm asking on the analytical side, is there any hope of trying to get the corrections to this twisting approximation?
So yeah, people, so in the modeling, they always try to improve how they can make it more accurate. So one thing that they are trying to do, so when you take this Allen spin waveform as your co-precessing waveform, so instead of fixing your initial spin here, you can vary the spin such a way they can like match better with the co-precessing waveform. So that one thing people do, and they studied that using this thing, using varying the spin component over time, that helps the accuracy. So that is one thing that we are also currently doing.
But the varying the spin in some simple way, like you just oscillate it or something? Or?
Yeah, so you see there is some oscillations here in the co-precessing frame. So when you take this approximation that co-precessing and Allen spin is identical, you are not considering this extra modulation. So yeah, the varying spin approximation that does do vary the spins in the Allen spin one. Yeah.
Okay, thanks.
Any more questions here?
I can hear it.
Hi, thanks for the nice talk. I just want to understand between your initial started one and when you sort of reconstruct the twisted aligned spin one, what sources the error? Is it the way you construct this R of T matrix?
Yeah, yeah. So there is two sources of error. One is the rotation that you do for the co-precessing frame. So there are different way you can track the precessing the frame. So one people do is tracking the maximum energy radiation direction. So that is one way. That is called the quadrupole. Just tracking the quadrupole energy direction, in which direction it's moving. Another way is to just track the instantaneous orbital angular momentum. So yeah, the error can be in the rotation that we are getting here, also in this co-precessing and align spin waveform mode that we are taking identical to each other. So yeah.
I don't think any. So thank you, Priyanka.